now. Okay. All right, guys, let's get back at it. Like Dave was saying, I'm another one of the Daves. I'm Dave Graham, like a box of crackers. A lot of you guys have already talked to me. Some of you know me from a little bit. Like Dave was saying, he's starting a whole new department within the company. So we've had 4 of us customer assurance people who can answer your phone calls, who come out on site visits with you, or do trainings like these. And Dave has been our head trainer for years and years and years. But now he's not going to blow his own horn, but what he's doing is pretty important. At the end of the class, we're going to have you fill out those evaluation sheets that help us to mold the classes into something that you'd like to see. And what most of the people have been saying for years is that they want a real hands-on class. So one of the things that Dave is doing is he is putting together a hands-on lab in the new Hudson office. And like I say, he's not one to blow his horn, but it's going to be really cool. So if you'd like to go and learn about how to do air conditioning and heat pumps, you're going to do everything from drilling a hole through a mock wall and running your line sets and hooking up your high voltage and your low voltage. And he's going to set up troubleshooting simulations where you're going to have to figure out what's wrong with a piece of equipment. And the same thing with furnaces, and they're going to be like 1, 2, or 3 day classes that you can go to. And it's a lot better than going 2 or 3 states over in order to get that type of a class. So it'll be really helpful to you guys. That is, he's going to start that up in the middle of the year, and we expect that's going to be a really big success. So because he is going to be dedicated to doing that, you're not going to be able to get a hold of him like you were in the past. I know he said that some of the time we'll be out doing site visits, some of the time we'll be doing classes, but we try to make sure that there's at least 2 guys for you all the time so that you'll be able to get your questions answered. Like Dave said, leave us a message, because when we get done with these types of classes, we're going to have 40 messages that, or 40 different phone calls that people have made, and we're only going to answer the calls that actually left us a message. Okay, so now we're going to move into heat pumps and air conditioning, and so our first point here is that it's all about moving heat. So air conditioning and heat pumps are appliances we use to move heat from one place to another. And in the summer months, we want to move that heat from the indoors to the outdoors, and in the winter months, we want to move it from the outdoors to the indoors. And so heat is a relative term. We talk about heat, we talk about cool, but there really is no such thing as cool. It's just the absence of heat, or a lesser heat than you had before. So heat is our relative term that we usually work with. And so we'll start out with, well, how hot is hot? Is 80 degrees hot? How about 120 degrees? Is that hot? Well, yeah, if it's 120 outside, I would like to get inside where the air conditioning is working. How about 500 degrees? That's got to be hot. You can always add more heat to the equation, but just for oh, by the way, the sun's photosphere has been estimated to have a temperature of about 10,000 degrees Fahrenheit. That's pretty hot, and some stars are hotter than other stars. So it's all relative. How hot is hot? So here's another heat is relative type of thing. That little thing on the top, that little silver doodad there, we're talking about the heat of the planets. And if you'll notice, the order of the planets is pretty much right, except we have Venus on top and Mercury underneath that. Well, isn't Mercury closest to the sun? Shouldn't that be the hottest thing? Well, it would be, except the atmosphere on Mercury it was either never there or it all boiled off. So it's just a rock, and it heats up and it cools down. But Venus has a really thick, acidic, volcanic type atmosphere. It's got pressures that are like 900 pounds per it's a really high pressure, high temperature atmosphere, like a volcanic atmosphere, raining acid and all kinds of stuff like that. Well, that little Venera probe up there was one in a series that the Russians sent to Venus, because of course we want to keep up with the space race, and they had Sputnik, and they had they were preeminent in the space race at that time, and then we came up with different things. We landed on the moon, so they were going to one-up us. Well, if you land on the moon, we're going to check out Venus. And so they sent a bunch of these probes. This was Venera 13. It was launched made it to Venus in 1982. And we only have 6 pictures of the surface of Venus because the atmosphere is so pressurized and so corrosive that everything burns up, melts, just turns to junk. So that's just a interesting, oh, by the way. But you can see as far as temperatures being relative, here on Earth, we think that 75, 80 degrees, hey, yeah, that's getting a little bit warm. But on Mercury, the temperature can go over 800 degrees, and on Venus, it can go almost 900 degrees. And so what we would think is a lovely, cool, refreshing drink of lemonade here on Earth, on Venus, maybe molten lead might be a cool, refreshing drink because it's plenty hot there. So you can always add heat to an equation, but there's only so much you can take away. So how do we cope with heat? Air conditioning, woohoo! And here's your basic air conditioning cycle. We always start at the compressor, and we see that we're taking a lower pressure, lower temperature gas, and we're squishing it into a smaller space, which is we're going to have some heat added by the compression to begin with, but then we're going to send that hot spitty gas out to the condenser, where we're going to try and take that hot spitty like gas, and we're going to try and condense it down into a liquid. And when we do that, you can see our outside temperature is 90 degrees, our inside temperature is 75, and our coil temperature over here is 105 degrees. Well, heat always moves from hotter to colder, just like moisture always goes from wetter to drier. And so when we have that hot spitty liquid coming outside, we run it through the condenser coil with the fan blowing the 90-degree air through it. But relatively speaking, 90 degrees is cold compared to our coil temperature. And so we're blowing the air through that, and we're releasing some of that heat into the outdoors, and we're cooling down the refrigerant that's in that coil, and it's going to convert it into a high pressure, lower temperature liquid. It still feels warm to the touch, and that's what a lot of people get confused about when they're new, is that, well, if this is the cooled refrigerant, how come it feels warm? And I tell you, when you're brand new to the field, you think like, well, oh, that suction line, that's cold. So obviously, everybody knows the compressor is putting cold gas or something to the evaporator, and then that's what makes things cold. And no, actually, it's that warm feeling liquid line that's actually got the column of liquid that's been cooled by the condenser, and now it goes to a metering device, and when it expands, it's going to start absorbing heat because it's going to increase in volume, it's going to lower in pressure, and when it does that, it's able to absorb heat when we blow air through that other coil. And then it goes back to the compressor, and the leftover cold feeling gas is really full of heat. It just feels cold to the touch, and it aids us in cooling our compressor so that stuff doesn't overheat. And that's your basic air conditioning cycle. So air conditioning components: contactors, capacitors, compressor, condenser fan motor, condenser coil, liquid line dryers of all varieties, metering devices, evaporator coils of every type and size, evaporator blower motors. So, and you guys know what's out there in the field. This is not the extent of it. There's all kinds of weird variations on a theme. So what is a heat pump? A heat pump is basically the same thing as an air conditioning system, but it can operate in reverse. A heat pump moves the heat from wherever it's unwanted to where you want it. And so cooling is cool temperature is relative as well. So how low can you go? Is 32 degrees cold? How about 0 degrees? That feels pretty cold. And this picture is of a guy in Antarctica, the coldest spot on Earth, with a record low temperature of negative 167.6 degrees Fahrenheit, which is still 292 degrees above absolute zero. So there's plenty of heat in that picture. You could boil water with the amount of heat that you have left in that picture, even though it's the coldest place on Earth. It's just a matter of getting it out of there. So cold is relative too, but is there an absolute cold? Yes, there is. You probably remember from your science classes. It's called absolute zero. It's the temperature at which all heat has been removed and all molecular motion is stopped. So we can keep adding heat into a situation almost as far as you can go, but as far as cold goes, once all the molecules stop, that's our absolute zero temperature of 459.67 degrees. And then that leads us into our basic heat pump. So we're back to our compressor to begin with. Our basic heat pump, we're compressing our gas. Again, only this time we're running it into our evaporator, and then we're running it from the evaporator after it relieves its heat into the house, and then the leftover heat goes outside where it goes into the condenser, where it gets through another metering device and it is expanded, and then it releases its 5 degree, or excuse me, it's able, as it expands, it's able to pick up temperature from the 20 degrees outside, because relative to the 20 degrees, the 5 degrees is colder. And so it goes back to the compressor and is compressed, and the cycle starts all over again. Well, it's not exactly that easy. There are additional components that you're going to have with a heat pump. You might have crankcase heaters to keep your oil and refrigerant warm when it's cold feeling outside. You might have suction line accumulator, liquid line receiver. Defrost boards is something new that you're going to use on a heat pump, because as you're picking up that heat from the outside, you're actually chilling the surface of the coil outside, and if there's any moisture in the air, it's going to start frosting the outside of that coil, and that frost will build to the point where it's going to block the air that's going through there, so occasionally you have to defrost that coil. So you'll also have your defrost boards on there, and then a second metering device. And most cases it was a piston on the outdoor unit that was metering the refrigerant into the house for heating, and then you would feel that your suction line was feeling like it was getting really hot. If you ever grab a hold of your suction line on a heat pump, you're going to notice, hey, that thing gets hot. And it's something that's gradual. It may start out feeling warm, but then it's going to build and get hotter and hotter and hotter for you. You got to be careful about how much refrigerant you put into heat pump systems. Well, all systems in general, but heat pumps in particular. I remember when I got my 284, that's that great big giant unit we've got over there. It's a variable speed heat pump, so it's not limited by 5 stages. It's got the whole complete range that it goes through. And there are special considerations that you have to put into those things, like because it's a heat pump, you want to make sure that the winter snow accumulation will be under it, so you got to jack those things up in the air on a stand or connect them to the wall or something like that. The 284 is a great big heavy 400-pound unit, so you're gonna put that up on a really heavy stand so that the snow won't build up against it, and when it goes into defrost, it'll actually melt all the frost off of the coil, and it can drain out of the unit completely, and you'll be ready for the next cycle. If you put them right on the ground on a platform or something, then they can't thaw completely, and eventually you'll get ice buildup on the bottom, and it'll actually crush into the coils, and it'll crush into the fins, and it'll ruin your outdoor unit. So for a heat pump, you're going to have a second metering device, so that it'll meter going one way, it'll meter going the other way. And there's all types of various devices that you'll have on that. So if we're building a heat pump system, we've got our compressor, condenser. You don't always have to have all these components, but you might see them. Liquid line receiver, filter dryer, sight glasses, expansion valves, accumulators, and the receivers and the accumulators, those are because depending on the temperature that it is outside, sometimes you need more or less refrigerant in a certain area. What you really don't want to do is take liquid refrigerant and send it to that compressor, because you're going to kill the compressor. So you put in things like receivers and accumulators to maintain the balance of where that liquid refrigerant is, so that it is enough to do the job, but it's not so much that it's going to kill your compressor. So if you see those, that's what it is. If you've looked at the mini split compressors, you'll see the compressor itself, and then you'll see this little thing next to it. That thing next to it is a is a secondary accumulator. And the primary one, you might see on one of the bigger systems, you might see a larger can that's a primary, and the one that's near the compressor is a little secondary. So back to the question, I already showed you the answer, but what's missing from this? Yeah, what's missing here is the most important and revolutionary device that has to do with heat pumps, which is the reversing valve. And the reversing valve is a really cool thing, and like the rotor on top of a helicopter, I don't know, these guys must have been total geniuses to come up with this stuff, because I would not have thought of this. But here's one example. Dave's got us another example over here. And you have a solenoid coil, and you have a little pilot valve right here. And the pilot valve has tubes that come off of it that connect to each of these other arms that come off. You generally have one little tube right here. That goes to the discharge line on the compressor. And so all your discharge goes through there. And then you'll have three other tubes. And in the pictures, you can see them mounted like this. You can see them mounted upside down. So you just have to pay attention that the small line coming in, that's the discharge line. And then your suction line is generally the one in the middle. And then one of these will go to the evaporator, and one of these will go to the condenser. And then inside of this device, when you energize the coil, there's a slide on the inside of this that will slide back and forth. And it will change the direction of the refrigerant. So you've got your discharge line up here, your suction line here, and then one line going to the condenser, one to the evaporator. And this is what it looks like on the inside. You have this pilot valve over here, and then you've got your slide mechanism. That's what this is on the inside. And if you're ever wondering what is going on with your reversing valve, I like to tell you, sometimes people want to condemn these things. Hey, it's not working right. It's got to be the reversing valve. I'm not seeing it doing anything. You can check them a couple of different ways. When you plug in the coil to one of these, when it's supposed to be energized, for regular split systems that we have in America, these things are energized in cooling, and they default to heating. So you wouldn't expect in the wintertime that this thing would have power to it, but in air conditioning season, you would get 24 volts or whatever the voltage is on the side of the coil that would go to this. That would energize it. But when you're talking about mini splits, it's a different animal. Those default in the cooling position. And so when we want to heat with them, we actually have to energize them in heat. So that's a little bit of difference between the mini splits and the standard ones that you get. Now I've got a little neodymium magnet, a very strong magnet that I can put on this brass right here, and you can feel where it grabs a hold and where it lets go. But that's another way you can test them. When you energize them, if you have one of these magnets that you can pick up at a hardware store, that magnet will slide back and forth to show you that that slide is actually moving. And then, of course, when you're energizing it and taking the power away from it, you're going to hear that characteristic psh. It's really fast. You'll hear psh, psh, going one way or another. Bloop. And just one thing about the coils on these, we're going to talk about motors, stepper motors. Motors, you can have them off of the device that they're connected to, and it won't harm them if they're energized. But coils that are on solenoid valves, which is basically what this is, a solenoid valve, you can't energize these things when they're disconnected, because they have to be under load in order for their magnetism not to overheat and kill the coil. So for coils on reversing valves, you've got to make sure that you don't energize them when they're disconnected. So here's how the things work, and it's really pretty neat. Your compressor discharge comes in here, and you'll notice that you have little pilot tubes drilled through both ends of this, and then you have these that when they slide to one side or the other, they have a path that the gas can come out of. Now, when that pilot solenoid is energized, when the compressor discharge first comes up into that container inside of the reversing valve, that gas can go equally in either direction, and it's sealed here and it's sealed here. So gas could leak out of either one of these tubes through here. So you got pressure coming up here, it can go around the outside of this, and it can make its way to either side. Those little tubes that you see connected to that connect to the pilot solenoid, they make it so that it's going to plug up one end or it's going to plug up the other end, so that you won't be able to have refrigerant pressure go through that end. And as a result, the refrigerant pressure will build up on one end, and it will slide the solenoid this way. And, or not the solenoid, it'll slide the, what do they call that, the slide? But if you plug it up on this end, then it's going to move in this direction, and it happens really quickly. It's surprisingly fast how it does that. So here's that, here is that pilot solenoid that we're talking about, that when it is in heating mode, it's plugging up this line. So when the discharge pressure comes up here, some of that pressure can go through this and some of that pressure can go through that. But because we've plugged it here, pressure builds up on this side and forces that over into and connects these two sections. And that's because we're not energizing the solenoid valve. This is the resting state for our normal split system heat pump. In resting state, there's no electricity here at this coil, and this piston is all the way over here blocking this end, so it shifts over into heating position. So in heating mode, we block this end, we've got our discharge pressure coming up here. Our discharge pressure can go through here and go all the way back into the suction line. So it's got a path for the gas to escape on this side, but there's no path for the gas to escape, so it builds up pressure and shifts this in that direction. And that's how that thing works. And that's just awesome. That's just really awesome how that works. And then in cooling mode, when we do energize that coil, it pulls this piston over to this side. It blocks this side. The gas still can go up either side, but now this side is blocked. It shoves this over this way, and it makes this connection so that we get our suction line connected to our indoor coil, whereas before our suction line was connected to our outdoor coil. And then that's how we switch between heating and cooling. And that's what a reversing valve does, and I think it's awesome. I think that's really awesome. So any questions on how that works? Nope? Good. Good job, Dave. Everybody knows just like that. Yes?
Last time we did a training up in Traverse City, you said you've only had a few fail.
Oh yeah, the fail rate on reversing valves is so crazy slim. I've been doing this for more than 35 years, and I've seen 5 fail ever.
How did they fail?
Getting jammed up, or most of the time it's contamination in these little tiny lines that it won't let the refrigerant flow through there. So it's usually contamination. But they're about the most dependable part on a. They're really extremely dependable. So if you're thinking, oh, got a bad expansion valve, think about it a little bit harder, because they're really very, very dependable. Okay, so here's our heat pump cooling cycle. So you already all know about the air conditioning cycle. So here's our heat pump in the cooling cycle. So I know that our suction lines are usually toward the bottom, and our liquid lines are toward, our discharge lines are toward the top. They just made this diagram easier so that we could know what's going on. So we've got our compressor, and it's got our discharge coming down here, and our solenoid in cooling has to be energized. So our solenoid on our reversing valve is energized, and so our discharge gas comes out, our discharge comes out there. It goes to our outdoor coil where it is cooled and condenses into a liquid, and then we get to this point. This is just to make it easier for you to understand what's going on in your thermal expansion valve, because nowadays you see them and it's all built in one and you really don't understand 100% what's going on with these things. But there is a check valve inside of here besides having the metering device. And so there are actually systems, I could show you some pictures, I didn't bring any, but where there's actual systems out there where there is an expansion device and a check valve and they're physically separated from each other. And it's really pretty cool to see that. But so in this example where we're in the cooling cycle, it's just like the air conditioners you're used to. So we've got a column of liquid coming this way. It could go through the expansion device or it could go through the check valve, and this is wider open. So, you know, it's always going to take the path of least resistance. So it goes past this check valve, encounters this other one that's going in the opposite direction. It stops there and that forces it into the expansion device where it flashes to a low pressure, low temperature gas, which goes into our indoor coil. And then our indoor coil is going to be picking up heat, and now we're going to be returning that low pressure, low temperature gas through the reversing valve back to our compressor to start over again. So yeah, in our thermal expansion valves now, we've got check valves and expansion valves, and they're combined in one. And oh, by the way, is that we're going to talk about how these work too, but basically the bulbs on here, I've had people tell me, oh, is that filled with mercury or something? It's like, no, it's actually filled with the refrigerant of the type of system you're working on. So if it's a 410 system, this is full of 410. If it's 454B, it's 454B up in there. That's why these things, even though they're close, you can't exchange one for the other. You've got to use the one that it's meant for it. Comment?
Yeah, one other thing on the expansion valve, because that bypass he's talking about. So just know if you're replacing one and it's going on a heat pump, it is that bypass valve like that.
Yeah, because they look the same. They look the same, but if you are going to use it on a heat pump, your heat pump expansion valve is going to have to be bidirectional.
Well, it's a bypass. So there's one that will meter in both directions. Some of our geo equipment only has one valve, but most of the BRYANT equipment is going to have one a valve or meter device in both ends. But that will just bypass in the opposite direction.
Alrighty, so here is the heat pump and the heating cycle. It's very much the same thing, except this time our reversing valve is reversed. This is in its resting position. So the discharge comes out of there, goes through the reversing valve that is not energized, solenoid's not energized, goes through the indoor coil. It picks up some temperature, and then the check valve in this direction, it heads up, it hits this other check valve on the other side, so it goes through the metering device, and then it goes out to the outdoor coil and back to the compressor again. So we're going from a high pressure, high temperature vapor down to a high pressure liquid that's been cooled, down to a flash gas that's low pressure and low temperature, and then finally back to a low pressure, low temperature that's going to go back to the compressor. Whoop. So on many of the legacy line condensers, you're going to see that you've got 3 ports. Well, what's this other little line for? That other little line is that if you hook up your gauges to your high side, your liquid side and your suction side, that's fine for air conditioning, but when it turns around and goes to heat pump, you're going to, because the flow reverses, you're probably going to blow your low side gauge. So you have a suction port that is going to plug into the suction line near the reversing valve. And so this is always suction, and sometimes this is liquid side and sometimes that's the liquid side. I mean, it's not really liquid, it's a vapor, but it's hot gas. So it's this is what you attach your suction line to, or your suction line on your manifold gauge set gets attached to that point. And then your liquid line, you're either going to put it on this side or you're going to put it on that side. You're going to change depending on what it is. And then this is a special valve that has got a hollowed out section here under this orange cap that is going to contain a piston metering device that the flow will change so that sometimes it will bypass and sometimes it will meter. But that's what that funky valve is. And we have our BiFlow TXV, And this is kind of hard to see, but this little seat here, you can see that it's up in this section and down in that. It's just to give you a better idea of that check valve operation that's going on inside of the TXV. So, okay, the heat pump defrost cycle. Now this unit is getting ready to go into defrost. You can see that we've got frost pretty even on the whole coil, and that's good. If you come across that and you're going to go into defrost, that's what it should look like. It should look pretty good. And it's okay if you have a little bare spot here, a little bare spot there. That's not a big deal. We'll talk about a little bit later of when you know that there's a problem by looking at the frost pattern on the coil. And so more moisture in the air, like in the beginning of winter and toward the end of winter when we have a lot of moisture out, because normally in the coldest winter it's going to be very dry outside, and you're not going to have as many defrost cycles other than it's just getting colder. But when there's a lot of moisture in the air, when you're using the heat pump to heat the house, you're going to get a lot more accumulation of frost on that unit because there's so much moisture outside. So one thing you want to be careful of is that your unit is high enough up off of the ground so that it can actually drain, like we talked about. So this would not be a good installation because the snow is getting up inside of it. So cooling mode is basically used to defrost, minus the outdoor fan. So, you know, when we go to defrost this unit, we're basically going to put it in cooling mode so that the heat goes outside and it will warm up those frosted coils, and then the water that results can drip off of the unit. We turn off the outside fan so that just the heat can be out there, but it's not going to have air blowing through it. You're still going to have the airflow on the indoors, but the outdoors we're going to shut off the fan and we're going to put it in cooling mode to thaw out those coils. So how do we do that? There are a variety of different defrost boards that you're going to see, and the defrost boards are going to come with a standard timing on them, but then you'll be able to use dip switches or little jumper wires to alter the defrost timing. I don't know if you can see it on here, but if you jump out, or depending on what switches you set, you can set it for 30 minutes, 60 minutes, 120 minutes, 90 minutes before that defrost will turn around. And then the same way on this other style board. And there are very many of these defrost boards. So even though now you've seen what these two look like, there's going to be a lot of varieties out there. So just be prepared to see that. So how do they do their defrost? One thing is they use a defrost thermostat. In this case, it's a little disc like you would have on your fan and limit switch on your furnace, only that one's inside of a little can. Here's one inside of a can. And then there's also outdoor coil thermistors that detect the temperature of the refrigerant. And that all has to do with the equipment being able to understand when it needs to go into and come out of defrost. So dip switch selections on those you can select the ones with dip switches. You can select of the BRYANT units all the different times that we said that we could do. They also on these boards have some jumper pins where you can short them out momentarily, and then it will speed up the cycle so that you don't have to sit there and wait for 90 minutes or 60 minutes or 30 minutes. It will substantially speed up everything so that you can check your equipment and make sure it's working properly, or troubleshoot things that are going on with it. Because everybody knows you don't want to be sitting there waiting in the snow for that thing to go into defrost. Yes? There are different temperatures that they go in, depending on what equipment you have, their times and temperatures will be different. On the Evolution Connects and the what they call perfect defrost, they actually, instead of having a set parameter of what they're going to be set to, they will have, if your defrost time, but by the time when you go into defrost, until the time the thermostat on the unit reaches a particular temperature, could be 32, could be 47, it's going to check that coil temperature, and when the coil temperature exceeds what that defrost temperature is supposed to be, then it will be able to be put back into service. With the Evolution Connect's preferred defrost, if we go into a defrost and the defrost takes less than 3 minutes, then the next time it's going to go into defrost is 120 minutes from now. If it takes between 3 minutes and 5 minutes, it's going to have the next defrost at 90 minutes from now. If it takes 5 to 7 minutes to thaw that coil to get that thermistor to reach that particular temperature, whatever it's asking for, it's going to take 60 minutes. And then if it takes greater than 7 minutes to defrost that coil, it's going to schedule the next defrost at 30 minutes. So that's a lot of nice variation that'll make your system work a lot more custom. So our defrost cycle, like I said, it turns off the outdoor fan, it puts it in cooling, and then it starts to thaw the outdoor unit. Sometimes when you get that switch over to cooling, you'll have customers that say, hey, my air conditioner or my heat pump sounds like it's broken, because it'll make this big whoosh noise. On some units that we have something called quiet defrost, where it switches more slowly so you don't get as much of a whoosh noise. But on some of them, they'll make this really big swoosh noise, and then depending on the outside conditions, you might even see a bunch of steam rising up off the unit. Sometimes you'll get the call from your customer, hey, my unit's on fire, it's smoking out back. It's like, no, that's natural. You don't have to worry about that. That is something normal that you will see from time to time. And then the basic logic for how it does it, how it defrosts the unit. The logic opens the outdoor fan relay, so the outdoor fan turns off. The logic powers the O to energize the reversing valve to get it to go into cooling, so that it will put that heat on the outside. W2, if you have a W2 connected, will send a 24 volt to the furnace, so that it can help in defrosting the unit. Most of the time, you won't use the furnace to defrost the coil. They don't usually allow you to defrost the coil with the W2 call. If you have like electric backup heat, then that will get energized to give you some residual heat while you're in defrost, because if you had a heat pump set up and it wasn't connected like to a blower coil, if it didn't have electric heat backup, you can get it to defrost, but in defrost mode, it's not going to be, that coil on the outside is going to be where the heat is, and then the coil on the inside is where the cooling is going to be. So sometimes you get cold falling out of registers, especially if the equipment is up in the attic. It's not usually the case if it's coming out of the floor and your furnace is in the basement, because you know that cold feeling air is not going to push itself up out of the runs. So that's how that works. So air conditioning and heat pump best practices. Like we said before, your heat pump has to be on a stand above the expected snow level. Otherwise, you're not going to drain, and you might end up destroying the bottom of this unit. And then you could end up with a leak, and then you're going to talk to your customer about replacing the unit faster than it's supposed to be. Think about these things in the summertime, because think about your clearances, because how close are you to an exhaust coming out the side, a dryer exhaust from the furnace? You see that a lot of times where the dryer exhaust is sticking all over the outside of the unit. So that's, with a dryer, it's not such a bad thing, but you also have to be careful with your vent pipes that are coming out of the furnace, either concentric vents or your intake and exhaust pipes. That you don't want to point those towards your condenser, because that is a slightly acidic mist that's coming out of there. And if you point it at the condenser, it's going to start rotting out that coil. So, and a lot of other things, you know, some people think, well, as I come out the house like this, rather than going straight out and maybe hitting my coil, I'm going to turn it sideways. And so the plume of gas will come out sideways. But what happens with that a lot of times is the plume of gas, you'll actually see that make condensation, and after just 1 year, you'll probably be replacing the customer's siding because it'll make a big mark on the siding. It'll discolor it. If it's wood, it'll peel paint and do all kinds of fun stuff like that. So be cognizant of where you're terminating your exhausts and where you have dryer vents and other vents that might be causing interference. You want to follow the manufacturer's clearance instructions. You want to make sure you're not too close to a wall. You want to make sure you're not too far away from a wall when you're talking about mini splits or your other equipment too. Usually you're safe on the gable end side of a house where you got that peak. You're okay to put your unit right there. But sometimes that's not true. Sometimes water and ice can shift off the roof in those positions too. So if you put it on the gutter sides of the roof, if they don't have gutters and you see that little trail in the dirt where the water's dripped off the roof and it's made a little path along there, don't put your condenser in that path. Or tell the customer, if they insist on that's where that thing's got to go, you got to tell them, you need to put gutters on this above this unit so that it's not going to ruin the unit. Most people want gutters anyway. This unit over here we can look at. Some people would say, oh man, that thing is not defrosting, it's doing a terrible job at defrost, but you can tell that that's actually water from the roof dripping on top of it that is causing these long icicles. So this isn't a problem with a defrost issue, this is a problem with ice and water coming off the roof and landing on it. So be aware of what you're putting your unit under, and make sure you've got proper clearance. Again, you can see the grass comes right up underneath this thing, so that's going to rot that coil out in the wintertime when the snow gets to it. End coils. Like Dave was saying, on the 454B, we're not going to have end coils anymore. We're going to have the V coil. But you are still going to be working on 410A systems. And like Dave was saying, on a 410 system, they didn't allow the V coil to be on top of a heat pump. They would only allow an end coil. So we do still have some end coils that we can get. If you need a replacement end coil, you don't have to replace it with an A coil. We have some end coils here still that you'll be able to replace that with. But all the new 454B equipment is going to have a V coil on it. And if you're dealing with end coils, this is just in there to show you that if you were to take an end coil and sit it on top of a narrower furnace, like a 17-inch wide cabinet, that you can either put this little transition under it so that it gets airflow up around it properly. You can split the difference, that's okay. You can put your the part of your coil that doesn't have a good airflow through there, and you can just blank off the bottom. On this side, what you can't do is this. You can't put that end coil to this side because there's no way to get air up under this section of the end coil. So don't do that. And if you need these little transitions, you have dimensions so that your sheet metal guys can put those together, and we also sell these. So if you're in need of one, we have them. So the new V coils, I don't know how many of you have got a chance to grab a hold of one and touch one and feel one. They are put together like a truck. They are really cool. It's very much like the radiator on the front of your car. It's got little micro passages that go through it, and it's a very sturdy thing as compared to your other type coil. Like your other coil, you could take your finger and go across it, and you leave those lovely lines, and you hate the little children that think that's fun. Or if you've ever had to sit there and straighten out coils, that's a real big pain in the cheese. But these things have a current footprint that is smaller, more compact. There are fewer manual braze joints, like Dave was saying. It puts in the refrigerant on one side, it goes down one side of the coil, it goes around the bottom and up the other side of the coil where the refrigerant is gathered and then taken off as suction gas. It's easier to change out the coil. There is a lower system variability, lower pressure drops going through that coil. So your static pressure will be better. System charging is the same as what we do today, and there are more options for the condensate drain connections. Plus, this has a huge benefit. If you ever went to clean this coil because your customer didn't want to change their filters, you take that front door off, It is so easy to reach in there with a vacuum and a brush and clean all that junk off of there. Whereas this one, you know, you're fighting with taking off the little triangular panel and getting in there and cleaning that. That's not so bad, but getting in there to clean in there can be a nightmare. So if their blower is full of junk and their blower wires are covered in crap and the blower wheel itself is covered in crap, then you know your secondary heat exchanger is covered in crap and you've probably got a evaporator coil that's covered in crap. So when you see that, if they're on a maintenance plan or something, your maintenance plan does not cover cleaning. Your maintenance plan goes out there and covers discovering it. Hey, you want to get on a maintenance plan with us? Great. We noticed this. We're going to have to do this cleaning that's going to take a couple of hours, and you're going to have to pay for that. But if they've been on a maintenance plan with you for several years, and then you say, hey, this is dirty, we got to clean it, you got to pay for it, they're going to say, how come you didn't keep it clean all those years where you were working on it? So be careful. Be careful with that one so you know what you're talking about. And another thing that's great about the V-coils is that that aluminum coil is substantially lighter than the copper and aluminum coil. So here's a comparison that says the N3617, where the V-coil is 37 pounds and the N-coil is 48.5 pounds, a 23.7% reduction in weight, which you'll notice when you go out to the job. It's not bad changing them, and they're really rugged. And if they don't leak when you first put them in, they're probably never going to leak because those things are built like a truck. A good truck. Okay, noise. Noise is caused by improper installation for the most part, in case you have a compressor that's really got a problem and is broken and all banging around on the inside. But you want to make sure that you're not transmitting vibration from the inside of the unit into the living space of the house. So if, examine the house. It's like, do they have their entertaining room in their house where the television is? You don't want that condenser right next to that window, right next to that room. If it's their dining room, you don't want it there either. If they have a patio area where they do barbecue grilling or something and they're going to do some entertaining, you don't want to put your condenser there. You want to put it away from bedrooms, away from areas where they're going to be entertaining, and because if there's noise, they're going to want you to fix the noise, or they're going to want you to yank the thing out. And a lot of noise problems can be taken care of by following these instructions as to how to take care of it. You want to leave some slack between the structure to absorb vibration. And what that means is that if you've got a line set and if you like to make little tiny holes and then shove your line set in there really tight, that's not good, because that's going to transmit into that sill plate. That is going to vibrate that wood all along that wall. So make your holes bigger than your line set, put them through there, and then use something like silicone caulk around the outside to hold that thing in place and keep the rodents out. But it'll act as a damper itself to keep the noise down. So yep, when passing refrigerant tubes through the wall, seal the opening with RTV or other pliable silicone caulk. You want to make sure your tubing insulation is in good shape. Avoid direct tubing contact with water pipes, ductwork, floor joist, wall studs, floors, and walls. Basically float that line set through that space using strap hangers, or if you're having to run it in the attic, you don't want to lay your line set right on top of all of those attic joists. You want to actually suspend it from the members that are coming down from the ceiling, and then float that thing across there so that they can get in there with insulation. Because what's happened a few times is people have taken that line set, run up the outside of the house, go into the attic, run it right along the top of all those floor joists, and then cover it in 2 feet of blown insulation, and that actually holds it down on top of those ceiling members, and it can cause a noise that you can hear in the ceiling of the building. So don't do that. Suspend it, float it through the air. Do not suspend refrigerant tubing from joists and studs with rigid wire or strap. They have those little black those little black straps that we have that you can pull the end over and adjust them to hold that. And usually you see those, going right across the joist. I would prefer if you would actually use strap and hang those, because if those are too tight, you can introduce vibration into those basement floor members, and that could cause noise as well. Yeah, don't use any rigid strap. Make sure you don't connect your pipes to, don't use the rigid pipe hanger straps, because those can transmit noise. You don't want to connect it to ductwork. You don't want your line set connected to ductwork. You don't want it connected to the floor joist. You don't want it connected to water pipes or gas pipe, because all of those things, and I've seen every one of those, all of those things can start transmitting noise into weird spaces. So as much as you can, just float that line set through there with, hanging straps. And if you can use the little strap sleeves that connect to the straps, those will actually make it work even better. So here's a picture of it going through the wall. This is kind of tight because you still have, your hole is still too tight here. So you want your hole wider, and then silicone caulk around the outside of that, because you don't want any tension on that sill plate when you're going through. And then you're going to want to use straps on the bottom of it. Bigger hanger straps. They don't have to be metal. They can be plastic.
Did you have the one with the clearances come up yet?
I don't know. Nope. Okay, so charging is based on correct airflow. So adjust the airflow first. That's the most important thing. So you want to find out, is there proper airflow? Do you have 400 CFM per ton? So our bottom base level is 350 CFM per ton, but it's usually better if you use 400 CFM per ton. If you get a lot of noise in the ductwork because the ductwork is small compared to how much air you have to put through it, you might want to cut back on that. But in most cases, 400 CFM per ton is what you're going to figure. So 2,000 CFM for a 5-ton system. So improper airflow will affect the heat transfer and the evaporator. Low airflow will cause low suction pressure, frosting the coils, low superheat, bad performance. So you want to check external static pressure, and the refrigerant charge can not be properly checked until the airflow is confirmed. And then you want to check the temperature split as well.
Something we notice on new furnaces is a smaller furnace can handle much higher cooling capacity now. And so what used to be fine with leaving a furnace on high, our installers, now you're almost putting the blower speed to one of the lowest settings.
Yeah, and it changes furnace to furnace, and when you're going out there in the summertime and you're doing a full new installation, it's real easy to say, okay, we've got our blower levels set for air conditioning, and those are higher, and that's great. And you might neglect everything you need to do on the furnace side. You might just say, hey, the blower levels are set great for the air conditioning, so the furnace has got to be right, and that's not true. So you gotta go in there, you gotta set your gas pressures, you gotta set your blower speeds. So one good just rule of thumb for you is that your temperature split can tell you a lot about how your installation is going. So it's normal for your air conditioner to have a temperature split of around 16 to 20. If it's more than 20, then you probably have low airflow. And if it's less than 16, then you probably have too much airflow. So circle those, put a star next to it. Just make sure you check that on your initial installation, and that's a really good rule of thumb that you're at least in the ballpark of where you're supposed to be. So, we would take you guys do this all the time. I know you're taking your temperature in your return duct, you're taking it in the supply duct. Usually not right above the plenum, but we'd have to make the picture wider and include more ductwork. You generally want to go about 3 foot down your primary trunk line to get your air temperature where it's all mixed up nicely. And then you take your temperature there, not generally right above the furnace, because it hasn't had time for mixing and you're picking up radiation.
Look at that picture. Pretend there's a coil.
Yeah. No. So this is obviously not enough airflow because we had, or it could also be low on refrigerant, but this is a low on airflow. We don't have enough air going through that, so the coil temperature goes below freezing, and we start building ice. Then once ice starts to build, it slows down the air even more, and it leads to more ice. And so you go out to the house, you're out there to do a tune-up or something on the air conditioner is not working, you go out to the outdoor unit, and the compressor is covered in ice because the ice starts at the compressor and works its way back through the line set. Or you go downstairs and you see that the front door on the evaporator has got ice sticking off the front of it. Well, that coil is just a block of ice. You have to tell that customer, yeah, I know it's 100 degrees out, but we're going to have to shut down the air conditioner and you're going to have to leave it like that and I'll be back tomorrow. Because there's no way you're going to thaw this coil. And putting it in heat, having heat from the blower blow onto it, you'll probably go off on limit before you ever start melting this, and the water that comes off it, it's going to flood your blower. So just tell them, come down here and watch as this thing thaws. You're going to have water come out of it. If you've got anything down there that you want to continue to own, you better make yourself a dam of towels around the outside and change them frequently so that that doesn't happen when it's thawing. So what is static pressure? Static pressure is the resistance to airflow in the ductwork. You want the right balance of static pressure in your system because too much or too little can cause problems, including premature system failure and energy inefficiency. So if you've got a whole bunch of convoluted, crazy pipes, those are all adding, nice straight pipes make for better static pressure, and all messed up convoluted pipes means the static pressure is going to be higher. So what is total external static pressure? It is like blood pressure. There's a normal range that you should have your furnace running in. High blood pressure in our bodies can result in headache, stroke, kidney failure, heart attacks, blindness, even death. Low blood pressure can cause dizziness, fainting, passing out. Well, high total external static pressure in our furnace can cause low cooling efficiency, evaporator freeze-ups, cycling on limit, and premature death of our system. So you want to be pretty careful about how you set your static pressure before you even think about setting the refrigerant level. So static pressure in your duct. So there are two types of pressure. There's the pressure inside the duct. That's pressure that blows in every direction like blowing up a balloon. That's your static pressure. And then you have velocity pressure. That's the other part of our other component. You put the two together and you get total pressure. What you don't want to have happen is have your static pressure so high that you eat up all of the pressure that your fan can deliver so that there's nothing left up for velocity pressure to actually push that air through the system. Different things contribute to the static in your system. The pressure drop caused by other items attached to your furnace could be your registers, your ductwork, filters, evaporators, coils. And so where we check our total external static pressure is at the blower, after the air filter, and before the coil. So it tells us what the pressure is inside the box. And the factory set that up so that the normal pressure inside the box is 0.5 inches of static pressure. When you start looking at the different pressures and different points of this, it's kind of like using a flashlight, because if you put your pressure probe over here, it's going to see everything back from wherever it was. If you put your pressure probe here, it's going to see the coil and the ductwork and the registers. If you put your pressure probe up here, it's going to see these registers downstream. It's not going to see any of this. So that's how we get our total external static pressure. And what we use to do that is these little tubes connected to our digital manometer. And this is a Testo, and it has been really good to me. I've dropped it, kicked it, stepped on it, and it's about 10 years old and it's still working great when I compare it to another scale. So to check the static pressure, we use these little pitot tubes, spelled P-E-T-O-T, pitot tubes.
Actually, they're not good tubes.
They're not? What are they?
Pitot tubes are gonna have two, you're gonna read both. Sorry.
Okay.
The ones we were using
Yeah, the ones that have got the long probe and it's got the other
you're-
gauge going into
you're
them.
subtracting.
So what do they call these?
That's just a static tube.
A static tube and a static pressure probe. Okay, so you'll notice.
Static tube had both connections on it.
So you'll notice they have a little angle on them and they have a point. Well, there's no hole at the end of the point as I'm going to pass these around, but there are holes on the outside of them so that the air pressure can get in there, and then they're connected by these tubes into your manometer. And so here's these, and here's that. So there's all kinds of different manometers out there. What we should be using right now is a dual channel digital manometer, but you know, you're always hearing about values expressed in inches of water column. Yeah, it says, you know, we want 5 inches of water column. We want 5 inches of static pressure. Well, this is one of the original meters. This is a water column manometer. It's got an inner tube and an outer tube, and it is it's a graduated cylinder, and it is ticked off in inches. So when they talk about inches of water column, this is what they're talking about. Is if you put pressure or suction on this, when you fill this up with water, the inner tube here is going to send a column of water that's going to bounce around, and it will equate to one of these hash lines on here, and that will tell you how many inches, physical inches of water column you have. So that's our inches of water column that they're talking about, and now we have digital meters to do the same. There's also incline manometers that we use. That had the fun red fluid on the inside that used to tip over and spill all over the inside of your truck, which was not a blast. Oh yeah, I know. I'm going to be 60 in July. Woohoo! I'm rather excited about that because that means retirement is just on the horizon. I am. I tell you what, I can still walk and kind of talk and chew gum at the same time. So far so good, but. I know. Well, I have less forehead showing than my dad, and you know what? They have an amazing device to take care of forehead, and it's called a hat. Spelled H-A-T, hat. Hat. And yes, I will be wearing a hat very soon. So, different types of manometers. We had magnehelic gauges and things like that, where we could check our static pressure. Like I was saying, ideally, you would take your pressures after the filter. Before the unit, but after the filter and before the coil going to this thing. But you can see it's not always easy to get in there because our filter is, you know, pushed up to the side really tight. Our coil boxes come down right on top of our furnaces. How are we going to get in there to get an accurate static pressure where we want it? Well, if you don't have a way to get in there, you can drill holes. You can drill holes into the furnace, but I would caution you that you want to talk to your customer first, because some customers are like my dear saintly mother who has passed. If you brought her a refrigerator and had one little teeny tiny scratch on it, she would have it sent back. And no one's going to put a scratch on my brand new thing I just paid a bunch of money for. So if you ask them nicely and you tell them why you want to do it, and it's to set up your furnace more accurately, most of the time, like your customer will be okay with it and say, yeah, go ahead. Just put some nice looking plugs in there. You know, if you need to use a bathroom, ask your customer. Just don't use the bathroom downstairs, because sometimes the bathroom downstairs doesn't work and the customer will get really upset with you. So usually you just ask them and say, oh, that one downstairs doesn't work. Use the one upstairs, and they're happy, you're happy, everybody's happy. So that's the same thing with putting holes in their furnace. Is you want to make sure that they know what's going on, why you're doing it, and they'll be happy with the result. So you can use the opposite side of the filter if it's open, if it doesn't have ductwork coming down. You can drill your hole in here. If you have, you can drill right through the front of the door when you take the outer door off. You can drill through the door, because it's important that you put your static pressure probes where that little hook, that little point, has to point in the direction of the airflow. So on the return side, if that return is coming down and going like this, you have to have that static pressure probe pointing into the airflow. And here up on top, you have to have that pressure probe pointing down into the airflow. So as far as your upper one, you want to measure down like maybe a ½ inch, and then you want to drill your hole into the side or into the back of the furnace. A lot of times I like it to be where you can't see it, So I will have that, that front of that furnace off. I'll take a tape measure across where all of the burners are, because that tells you where all of the cells are. And I'll take that tape measure and put it along the back of the furnace, and I go, that's where I want to drill. I'm not going to drill into a cell or anything like that. I'll be down about a ½ inch, drill a hole in there, point my pressure probe down, and then I'll be able to get my most accurate static reading that way. But always ask the customer if it's okay with them for you to be doing that. And we use the static pressure probes in our meter to check our total external static pressure. We measure just outside the unit after the filter and before the evaporator. One reading will be positive, the other reading will be negative. We want to ignore the positive and negative and just add those two numbers together. So if you're, depending on how you're set up with your the channels on your manometer, it might subtract one from the other. So be careful and make sure you have two raw numbers, and then you just add them together to tell you what the static pressure is. And like we were saying earlier, the company and most other furnace companies, Bryant, Carrier, everybody out there usually will set up their static pressure on their furnaces to 0.5. That's how all of our Bryants are. So we're looking for a 0.5 that will give us the normal amount of air that's being taken up by static pressure and the normal amount of air that will be going down into the duct as velocity pressure. So why is this so important? For about, I'm a little bit embarrassed about this, but not too embarrassed, because but for about 10 years I was in the heating cooling business, and I didn't know anything about static pressure, didn't know what it was, didn't know how to use it, but I would notice that I would go basically be doing the same job over and over and over and over, and the same job would work great on numbers 1 through 25, and then you get to number 26, and you did exactly the same as you did every other job, only this one didn't work. It'd be going off on limit, it'd be freezing the coil. And it's like, why? Why are you doing this to me? I've set you up just like I set everything else up. So the static pressure, like I said, is supposed to be 0.5. And so if you have really restricted ductwork, or if you have dirty coils, or the registers that they put in the floor, those little wooden ones rather than the metal ones that open properly, it can increase your static pressure. And when that happens and you're no longer at a 0.5 where you are supposed to be, and you're up 6, 7, 8, 9, even to 1, excuse me, you'll notice that the amount of airflow that you've got going through there is not the same as what you would ask for had you had the right amount of static pressure. So knowing what the static pressure is in the duct will let you adjust your airflow so that if you needed 1220 over here, but you had a high static pressure over here, you would have to find some other way to get that 1220. So you'd be adjusting, you'd be adjusting to level 14 instead of level 10 to get the amount of airflow that you wanted. So that's the big deal with the static pressure, and that's an amazing thing, and it's a really good thing to know, because if you know this, you're going to get proper airflows, and you're not going to get going off on limit. You're not going to get freezing coils. So learn it, live it, love it. This is very important. So if you don't have static pressure probes, yeah, temperature rise is an additional check you can do, and that's what a lot of guys are used to, is like, all right, I set my gas pressure, I'm doing my temperature rise is in the middle of the range, I must be pumping enough air. So yeah, that is a good way to do that, but that's a great way to set up your furnace. But how do you know what your airflow level is with your air conditioning? You really ought to check the static pressure. Excuse me. So right now we're checking the return on this furnace. We're after the filter, we're inside the box, and we're getting a 0.3 static pressure in there. So far, so good. And then next, we're checking below our coil. So it's on top of the furnace, but below the coil, which is where we want it to be. But in this case, we've got a 0.7 static. And it's like, what? Why are you so high? Because we're shooting for 0.5. So 0.7 and 0.3, we've got 1 inch of static. So that other chart that we were looking at, that 1 inch of static, we're way over here. We've got really high static pressure. We've got double what we want. So we have a huge reduction in the airflow. So we want to figure out why we've got 1 inch of static. And we had a lower number over here, and we have a much higher number over here. Typically, these will be like 1.5 to maybe as much as 3 going through the evaporator coil. But we have 7 inches going through that evaporator coil. So we're going to find out that our static is way up, all the way up at 1. So if we had a 2.5 ton air conditioner that we needed 400 CFM per ton, on what airflow are we looking for? 1,000. Yep, we're looking for 1,000 CFM. So if we had 0.5 of static right here, we're looking for as close as we can get to 1,000 at 0.5. So, you know, we would be down here on our yellow wire on this particular moment. Sometimes it's dip switches, sometimes it's colored wires that we're going to decide what kind of airflow we're going to get out of this thing. But way up here at 1 inch of static, we're only delivering 760 CFM. We can try to get over that by switching to a higher level if we have one available. You can see in this example we have gray through red, and gray is our highest speed, so we're not getting the right amount of airflow through that unit. So we've got to do something about that. How do we get our static pressure down? We add more ductwork. Add more ductwork into the system. You find out, is the static pressure high on the return side? Add some more return. Is it high on the supply side? Add some more supply. Or put in a smaller furnace. Maybe that's the answer. Maybe the furnace, maybe when they did the manual J, they know how big the furnace should be for the house, but they didn't take into account the size of the ductwork, and so the ductwork is too small for the equipment that you put in. So hopefully your salesman is doing the manual J and the manual D to figure out how big the ductwork should be, how big the furnace should be. And if there's a problem, then you're going to have to add more ductwork to get this equipment to work properly. So pressure drops across the evaporator. In this example, it's a 0.18, which that's a reasonable pressure drop. And then some people have, if they can't get this reading to know what the static pressure is here, they will check the pressure drop across the coil and then subtract that out to see what the static pressure is on the furnace, but that's pretty much the same thing. And it's only accurate when the coil is brand new. And in your coil literature, you're going to have a wet coil and a dry coil, and you're going to check and see how much static pressure you have going through it, and then that can tell you how many CFM is going through that coil. So that's another way that you can go at it. So external static pressure, you've got your probes. The probes face the air in the direction they're going. This is showing a negative 0.2 on the other side of the filter, but on top of the coil we have a positive +3. We add them together, 0.5. That just tells me that the ductwork is really loose and wide open. So if the ductwork is really loose, because we're supposed to take this reading from here, and they took it on top of the coil instead, and they go, oh great, we got 0.5. It's perfect. There's nothing wrong with it. But what that's meaning is that your ductwork is probably too big so that you may not throw the air properly all the way to the ends of the ductwork. Yes?
That last page, the performance data, where did you get that information?
Oh, this data? It'll be in your coil instructions. It'll come with the coil.
Before you move on, does everybody got Service Tech app on their phone? Okay, so if you scan the coil or the furnace or the rooftop, whatever, it'll take you to all the literature. Okay. So that's all right there. So it's all readily available to you now.
Okay.
Cool.
Thank you, sorry, David.
Yeah, and I know that's great. Yeah, and that's a great point, is that everything is covered with QR codes right now, or scan labels, and that's a really beautiful thing, because you used to have to go hunting for it, and you may not have the exact match you're looking for if you're like going through HVAC Partners. But if you have a QR code that you can scan, it'll take you to the specific literature just for that furnace or air conditioner, which is fabulous. Fabulous. So coil static pressures, you know, like we were talking about before, we have a 0.25 in this instance. So this is the coil we're talking about. 0.25 would equate to 1100 CFM. And that's how you use those charts. And generally you will see lower numbers when you're going across the coil. If you see high numbers when you go across the coil is full of crap. Okay, temperature rise method to calculate CFM. So when we're doing the furnace, your basic test is going to be just to take the temperature rise and see if you're in the middle of the range. But this is to actually give you a calculation to know what the actual CFM going through that unit is. So you turn it on, you allow the system to stabilize, you make sure the system is not cycling, and you measure properly. So you're going to be measuring return temperature, supply temperature. Your furnace temperature rise should be close to the middle of the range on the tag. Each tag is different. Some have, it'll be somewhere between 35 and 75 degrees. And you just want to try and be in the middle of that range so that if the filters get plugged up a little bit, it's not going to mess things up. So middle of the range, you're usually in good shape. So here's the formula. Your BTU input times your combustion efficiency divided by a constant of 1.08 times the temperature rise gives you the CFM. And in practical application, here's how you do it. 100,000 BTU furnace. Furnace is 92% efficient. You got your constant of 1.08 times a 55 degree temperature differential, or delta T, comes up with 1,594 CFM. So you know exactly the amount of CFM that's going through that. So that's a handy thing to know. So if you don't know the airflow, excuse me. So if you don't know the airflow on a system, and you're not going to take it, you should always weigh in your charge, because if you don't know what the airflow is, then weighing in the charge is the safest bet. So you would weigh in a refrigerant charge that's on the side of the unit, and then you would add for residential units, they're set up for 15-foot line sets. Anything beyond that, you have to add those amounts of refrigerant per extra foot of line set that you have on there. So for 3/8 line set, you're adding 0.6 ounces per additional foot. For 5/16 line, it's 0.4, and for 1/4 inch, it's 0.27. And that's the same as it was with our 410A. It's the same as it's going to be for 454B. Excuse me. Charging a system. Always liquid charge, blended refrigerants. 410A and 454B are blended refrigerants. Where if you were to charge with the jug upright, then we have our refrigerants boiling off at two different temperatures. So you would boil off all of one of the components first, and then you would boil off all the other components second. You'd be left with only one component or the other, or an oddly mixed blend. That's why we put them upside down and we run them through a charging adapter, or send very little amount of refrigerant through there so that we don't slug the compressor. But you can send a little bit of liquid and it'll flash inside your line set, or inside your line going to the condenser. Excuse me. This little thing here, that's sometimes you see these as little silver pieces. That is just a tool that they use to flash the gas, or flash the liquid into a gas before it goes into the. Yeah, it's like a metering device. It's a little bigger than a normal metering device, so you can fill it in there. But a lot of guys swear by these things and love them, so they can charge the maximum they can at a time. You can usually listen to your unit while it's running, and just burp little bits of liquid in there and let it flash so that you're not hurting the compressor. If you hear a drastic change in tone, if it's like, then you know you're filling too fast and you got to slow down. I saw that smile. So what is the subcooling method? It is the preferred method for checking the charge on a system with a TXV metering device. The expansion valve is constantly maintaining system superheat, and it's looking for between 7 and 14 degrees. So that's what you should be looking for too. So subcooling refers to a liquid existing at a temperature below its normal boiling point. So any amount of temperature below the boiling point of water, let's say 200 degrees, water has 12 degrees of subcooling. So this could also be stated 12 degrees below the boiling point. So water boils at 212, the water temperature is 200, so 212 minus 200 gives us 12 degrees of subcooling. And in this state, it's only liquid and there's no steam. So when you're doing the subcooling method, you have to have favorable charging temperatures. To properly check and adjust it, you have to have an outdoor temperature that's between 70 and 100, and you have to have an indoor temperature that's between 70 and 80. Sometimes you go out to these houses to do a startup and it's 95 degrees in there. You can run your air conditioner until you can get that temperature down, till it's within that range. You got to be 80 or below in order to actually do your final charge on that system. Sometimes it takes quite a while to cool off a house to get to that point. If you don't have time to do it, you can start up your system, you can go away and tell them you have to come back another day to do the final balancing of the system when it is going to be favorable conditions for you. Same way with the outdoor temperature. If it's over 100 outside, you can't do it.
Is there any risk of, like when we do an install and we, right now, and then we don't weigh in charge, and we don't get back there in time to run their system?
If it's drastically undercharged, you could freeze. You could freeze the evaporator. If it's overcharged a little, they don't generally. I mean, if you have a really tiny line set,
Yeah.
10 feet is the smallest you're supposed to put in there. So if you're a real small line set, there is a chance you might hurt the compressor, but it's very remote. So the outdoor unit contains the correct system refrigerant charge for operation with a factory-approved AHRI rated indoor unit when connected by 15 feet. For 15 feet line set charge, some units may require additional charge depending on size. You may have noticed in the literature that comes with your condensers that if you're having a small, like 1 or 1.5 ton air conditioner, that it'll say in there that the unit doesn't contain enough refrigerant for the whole system, including the 15-foot line set, and then you're going to have to add some refrigerant just to bring it up to the starting point. And it's usually only a few ounces, but you have to pay attention to that and add that little bit of ounces of refrigerant in there just to get it at the starting point. And then beyond that, you can consider what is my line set length and how much do I have to add for that additional line set length. But those are only in the very small units. And you'll normally see a note in there. So on the small units, read directions, make sure what you're working on. So to measure subcooling temperature of a liquid line, you cross-reference it with the liquid pressure on a temperature pressure chart. This one is for regular PURON 410A refrigerant. So to do this, we have our liquid line and suction line attached to our manifold gauge set. We have a thermometer on our liquid line, and we are going to convert our liquid pressure into temperature. So if we got a liquid temperature of, liquid pressure of 230 pounds, it converts to 78.5 on our temperature pressure chart. And then we take our actual temperature of 72 degrees on the liquid line, and we subtract one from the other, and we come up with 6.5 degrees of subcooling. So subcooling you do on the liquid line, superheat you do on the suction line. And they're pretty much backwards from each other. So this is another one of these, a flow restrictor to flash the liquid to gas on its way to the condenser, so you can get it in this style as well if you don't trust yourself to do it slow enough and you don't want to damage a unit. So you'll have a digital thermometer stuck on your liquid line, and pretty much the same thing again. So we've got 105 degrees of temperature, we have 395 pounds of pressure, and we look on our subcooling value that is on our sticker that comes with our unit, and it says indoor TXV subcooling of 10 degrees Fahrenheit. Sometimes you're going to encounter a tag that's not going to say anything. That's usually the high-end equipment that's going to be normally connected to a Connex thermostat, and then when you're doing your charging, you're going to specify what indoor unit it is. It's going to pick up, it's going to go look for it, it's going to find the indoor unit, the outdoor unit. You're going to tell it how much of a line set and what size it is, and then it's going to make the calculation for you and tell you this is what your subcooling you're shooting for, and it'll generally tell you how much refrigerant that it's going to want you to add. It'll tell you it'll tell you the starting charge and then what you're going to have to add to it if you touch that little spot on the thermostat. So in this case, we have 240 pounds of pressure on our liquid line. We have 70-degree temperature. We convert our 240 pounds from pressure into temperature. We subtract one from the other, and in this case, we have 11 degrees of subcooling. Everybody get that? How that works? You're already doing it already anyway. So you have just a refresher for you. A refresher is good. Sometimes you can go through a whole class and only pick up 1 or 2 nuggets, but that's a couple of things you didn't know before.
What's your acceptable range for the subcooling? You know, it says 10. I usually give it a plus minus 2.
I think they say plus or minus 3, don't they?
2 is better, but 2 to 3, because, you know, if you check it today and come back tomorrow, it's not gonna be exactly the same.
Yep. So superheat occurs when the vapor is heated above its boiling point, any amount of temperature above its boiling point. So 220 degree steam is 8 degrees above water's boiling point. So it could also be stated as having 8 degrees of superheat. There can be no water present, and then if the steam is superheated, there won't be any water left. It'll only be steam, because you're going to keep it a constant 212 degrees as you're raising the temperature of that water. It'll get to 212 degrees. Then you're going to have to add in 970 BTUs per pound in order to it to all go to steam, and then you can start raising the temperature again. So we have our 220 degree steam minus our 212 degree boiling point of water gives us 8 degrees of superheat. And then we use it pretty much the same way, only we would use superheat if we have a fixed metering device like a piston type or a capillary tube. Like I said, we're old, and so we even remember when line sets were, you know, just a copper suction line, and then they would have a real long capillary line, and it would be welded to the side of the suction line. So it varied by how much capillary tubing you had would add resistance to the value of the whole system, and it was a weird way of doing things. But that was some of the earliest ones. So fixed orifice or capillary tube, you'll be using the superheat charging method. So superheat, in this case, we've got, we would attach our thermometer to the suction line, and we would be concerned with the pressure of the suction line to tell us about superheat. And so we would use our superheat method for charging. It's very much the same as the subcooling method, only this time we're taking our temperature off our suction line. And that's actually drawn wrong. This temperature would be taken, okay, there it is. It's just this was an original picture. Don't look at that. Just don't look at it. Don't look at it. Yeah, and dual probe thermometer, we don't really care about that one. But yeah, the other one is going to the suction line. So we take our suction pressure, we convert it to temperature. In this case, it's 40 degrees at 118.0. And then we compare that to what temperature we're getting on our suction line. So 55 on our suction line, 118 on our suction gauge. So we converted that pressure to temperature, came out at 40. So we take our 55 line temperature minus the derived temperature, gives us 15 degrees of superheat. Everybody understands superheat and subcooling? Any questions? Sorry? Yes, you would actually be, this is just the basic method, but yeah, we would need to have indoor wet bulb and outdoor dry bulb for this, because I think we might have some slides coming up with a sling psychrometer. So you'll have a target superheat chart, and then you just, you'll find out that at outdoor temperature of 85 degrees and indoor wet bulb temperature of 62, and you're always going to notice that your indoor wet bulb temperatures are going to be lower than your dry bulb temperatures, because unless it's a very, very dry day, and then they might approach each other. But what it is we're finding out how much temperature there is in the air relative to how much humidity there is in the air inside the house. We used to, not going to show us, we used to use a thing called a sling psychrometer. It was basically two of those old style thermometers like mom and grandma used to stick in your mouth, and not the in the ear, up the nose, or any of those things, but your regular thermometers. And we used to have something like a little wick that would hang off of one of those ends of those. It was two thermometers that were side by side, and they called it a sling psychrometer. And it had, like, if you took a shoelace and cut a little web of shoelace off, and you could put it around the outside of one of the bulbs of those thermometers, and then you wet it with water, and then you would like fling it around your head so it could see how fast that water would evaporate, and that water would cause a cooling on one of the thermometers. And then you'd have the wet bulb and the dry bulb temperatures that you have. If your air was really dry inside the house, then it would cool that bulb off quickly, and you would have a lot of difference between the dry bulb and the wet bulb that you got in the house. If it was really humid inside the house and like it was getting ready to rain inside the house, if you did that, you would see a slight difference, because the wicking action of the water wouldn't be, since the air was not dry, there wouldn't be much water extracted, and there wouldn't be much of a cooling effect on one of the thermometers. So that's where they get wet bulb and dry bulb. Another.
Most of you probably thermometers, they'll call it hygrometer, but most of your thermometers will do dry wet bulb. You don't need to do, but you can actually do that. You take a pocket thermometer, like they've said, get a cheap shoelace, that's what we used to do, and cut a chunk of it off, slide it over, and wet it. Stick it in a return. It's the same thing.
Yeah, just the air blowing across it. Mm-hmm. Yeah, yep. So it's yeah, it really doesn't care what fluid we're using. So use your imagination, whatever you happen to have that's wet. Yes, exactly. So air conditioning service basics. Okay, so the metering device is located in the indoor coil of an air conditioner, or both coils of a typical heat pump system. The metering device creates a pressure drop that causes the temperature of the refrigerant to be lowered. This allows heat to be absorbed into the refrigerant. And we've already talked about that the bulb contains the refrigerant of whatever you're working on. So there are different forces that are working on the expansion valve. You have two lifting, and you have two opening and two closing forces. The first opening force is at the top, where that pressure is exerted on top of the diaphragm created by the temperature of the bulb and the refrigerant in the refrigerant charge in the bulb. So that's putting one type of pressure on top of the diaphragm, which is causing this seat to move up and down to open or close the amount of refrigerant that's going through there. And then we have a closing force. The suction pressure exerted underneath the diaphragm, that's a closing force. So we have a suction force underneath the diaphragm that's pulling us down. Then we have a closing force, the factory preset spring tension under there that's pushing up, that's trying to seal that off. Now you might have noticed on some expansion valves, they'll have a nut on the bottom of them where you can take that nut off, and if it doesn't spray refrigerant all over you, it'll have like a screwdriver slot in there, and you can adjust that pressure up and down. You're actually adjusting what the superheat value is. My advice is don't ever adjust them. Even if there's a nut down there, don't ever adjust it, because it's properly adjusted. If it's getting out of calibration, you may fix it for a day or two, and then the problem will come right back. So it's not worth your time. If you have problems with your expansion valve, don't even mess with it. Replace the thing. And then you have one final opening force, liquid pressure acting upon the pin area. This force is eliminated in the balance port, the balance tube construction of the valve. So the rules for movement on this is you add 1 and 4 together, and if they are greater than 2 and 3, the valve will move open. You add 1 and 4 together, and if they're less than 2 and 3, the valve will move closed. If 1 and 4 and 2 or 3 are equal, the valve stays in its current position. And it's just that easy. Pretty neat. Another interesting invention somebody came up with that's kind of cool. So sensing bulb position. Where are you going to put that sensing bulb? On small lines, you can, excuse me. Okay, so they talk a lot about 4 and 8 on this. It used to be, I mean, we used to hear terms of put it on 3 and 9.
All right, here, let me.
Yeah, go ahead.
Let me step in on this. All right, and I put this in there because this is always a bad thing, because there's always this big debate. Mickey Mouse ears, you know, might hear that, put that, you know, that 2 and 8, or 2 and 10. Okay, so this is actually from Portland. Anything under 5/8, any liquid line or suction line smaller than 5/8, it would be on the top. Okay, anything 7/8 or larger, it will be down where you see it there, which is 4 and 8. Because if I have a larger suction line, I could have liquid sitting in the bottom. So if I'm reading it up at the top, it's not seeing that liquid sitting down there. Now you don't want it on the very bottom because you're gonna have a little bit of oil right here. So 7/8 and larger, we're gonna go to the 4 and 8. And if it's smaller, it can be at the top, or you're gonna put it at 10 and 2.
What about if you see it at in the a vertical
In
position?
the vertical, the tube upward, like this. Yeah, if you have to put it in the vertical, this way. Don't mount it this way because, like he said, there's refrigerant in here. So if you have liquid or refrigerant in here this way, it's going to affect how this operates. So if you have to go on the vertical, this way. Now, when you install these, the other thing always questions me: do I insulate it? Yes, insulate it. Sometimes from factory they're not, but any outside temperature can affect this thing. So you want to insulate it, regardless. And then when you attach it, you should not be able to move this. You want it tight enough that it's secure, you can't see light through it, but on the other hand, you don't want to crush it. All right. And that being said, back to what Dave said, the 454B, the R32, and the 410 valves are all different. They have to be labeled for what they're for. Pressures are very similar, so I don't know how different they are, but they are different. Lastly, out of the pressures, go back to that other slide. Out of the pressures Dave was talking about here, one of them is evaporator pressure. Now, on refrigeration, we have what's called internally equalized. We don't use this tube. Rule of thumb, anything over 1 ton, we're going to have this equalizer tube. So, sometimes these are brazed in, right? And you're saying, screw it, I don't want to do that. If you eliminate this tube, you're eliminating one of the 3 pressures that operates the valve. Will not work right. So, just as much of a pain as this is, it's integral to the operation of this valve. Okay, so this one here has an adjuster on. Most of the OEM ones are going to be a flat top. That you'll see this nut's not here, it's just flat. Don't try to take that off because that's holding that spring in.
Now, my advice is don't take them off at all.
Don't try to adjust. I had a teacher once tell me 100 years ago, unless you saw, you had a priest and 2 nuns swear they saw somebody adjust that valve, don't mess with it. They're set from the factory from 8 to 12 degrees, which should be sufficient.
The only exception I ever found to that was like on some heat pumps. It might have been Bosch. They actually had it in the instructions on how they wanted you to adjust that valve. But other than that, everyone else says don't adjust it.
Bosch, now that you mentioned, Bosch does use a biflow. So some of our geos have a single valve, which is metering in both directions. They're the only one the only thing we carry that I know that doesn't. Yeah.
Now, most of the coils, they gotta each side. You replace it, you can put them outside, the coil?
The bulb? Yeah, you can. You want it as close to the outlet as the coil as possible. And if you're putting it on the outside, you definitely want it to. Yeah, because you're talking about this much distance.
Yeah.
So you can do it, but definitely right outside the cabin and insulate that bulb.
Is it better outside or is this better
No.
inside? Doesn't matter.
They put it inside because it's mounted from the factory. Sometimes you get different brands, the bulb is not mounted and it's hanging there, they want you to mount it. But yeah, mounted outside is fine, just make sure it's close to the cabin as possible and insulate, definitely insulate. So
Absolutely.
Because the basement air could affect it.
So checking the TXB bulb, if you were wondering whether or not the thing was working properly, you can take it off of the unit. You can use the heat of your hand to heat up the bulb and see if it will feed more refrigerant, or you can put it in ice water and see if it'll feed less refrigerant, and then you can pick that up on your gauges and see if it's affecting it. If you find out that there's not much of any change, you've got a bad expansion valve, and you should change it.
So when you do that, you see if it changes, I mean, if the TXV is okay?
Yeah. Yeah, if you see changes in pressure, then yeah, that TXV is okay. We don't do the, we're all completely out of the woods with the Zerol ice stuff, aren't we? Because there was a time when there was a sticky substance in the manufacturing that they put together, and we had to inject this chemical called Zerol ice into the system that would help to break that stuff up and make the TXV work properly again. But we're beyond that by several years now.
That was actually an inhibitor in the compressors.
The reason I tell you is I do a couple few times like that with the water, and I can see the changes. But when I put it back, they go like a stock again sometimes. Do you see that before?
Well, there could be something in the valve.
In the valve?
So when you hold your hand on it, it runs it wide open.
Yeah.
And so, but when it's running on the line, it's just barely modulating, so there might be some crap at that seat.
Yeah, that's not an end-all be-all test, but it's a pretty good test in most cases. But if you're getting results like that, then you probably are going to have to make a change. What's next? Well, if you want to say something about that, it's fine. We're almost out of time for my section.
No, nothing, I just say, because if you take the valve apart, there's just a little valve, there's a little hole in there, it's the valve itself, and then the seat is just a needle. So it goes up in there, so you get a little crap sitting in there, and it might keep it from functioning properly, but when you put your hand on it, it's enough to drive it wide open, so it looks like, best way to test the things, they're set from 8 to 12 degrees. We don't check superheat for charging anymore, but if the system's charged properly, you can check the superheat on the TXV, and it should be maintaining about 8 to 12 degrees. That 50, the charge is right, the valve's not working right. So that's kind of the simplest way on those to test.
Okay, so measurement points on these things. We're so used to doing our measurements on the outdoor units, either on our liquid line or a suction line to figure out what the temperature should be. But if you have an exceptionally long line set, then these temperatures could be off enough that it will affect how you're going to charge the system. In that case, you want to go inside and take your temperature, at least, at the evaporator coil to get a closer idea of what the temperature actually is. Sometimes you guys have those newer gauges that are electronic, and you can use repeater cells and things that you can attach to the ductwork so that you can still be outside. You can connect your thermometer at the indoor unit and still get the readings on your gauges outside. I'm old school. I don't use any of that stuff. I would actually go inside and put a thermometer on it and take a walk back and forth. And like Dave was saying, I've been with BY for 3 years now, and flying the desk kind of makes you fat. So it's a lot easier to sit there and find donuts and things around the office. So I need all the exercise I can get. So out in the field, not a bad idea to keep active. So anytime the line sits over 50 feet, it might be a good idea to start checking your line temperature on the inside near the evaporator. Compressor, checking the states of windings. I have a piston type compressor over here. We have compressor windings, scroll type compressor on the other one. So when we're checking the windings on our compressors, we have a run, a common, and a start. Run, common, and start windings. And the two readings should add up to the third reading. So between run and common, if in this instance we had 0.8 ohms, and between start and common we had 0.12 ohms, when we add those together, that's what we should get between run and start. And if it turns out that that's the truth, then everything is okay with that compressor. That's another way. If the cover on your compressor If you can't see the stampings on it and you're not sure when you've already taken the wires off, if it had individual wires you had to put on that compressor rather than having that fusite plug that you could plug in there where it was already done for you. Sometimes we used to have to figure out, oh, I didn't take a good picture of this and I don't know, the windings aren't marked, so how do I know which winding is which? This is how we did it. We would find out what was the lowest reading and we would know that was run in common, and our next lowest reading would start in common. So by a process of elimination, we could figure out which winding was which and put the right wires where they belonged. So if you ever come across older equipment that just has wires and nothing is marked, that's how you do it. So what's wrong with this compressor? We have run to common overload, start to common overload, run to start 0.2. What? Yeah, I think somebody said it. Yeah, thermal overload is open. That's what that little symbol up there is the thermal overload. The compressor got too hot and it shut down. You got to give it time to reset. If I came across that situation, I would feel the compressor and it's probably scorching hot. I would tell the customer that there's no way to cool this thing down properly in any quick amount of time. We'll be back tomorrow. And I would pull the disconnect at the outside unit so that the customer's like, man, it's hot tonight. I'm going to turn this thing back on. And then you go out there in the morning and the compressor is still burning hot because they were farting around with it. I would take out the disconnect and flip it around or take it with you, do something so they can't turn that system back on when you go back out to the shop.
Cooler. How did you put your hose on?
Oh, yeah. No. Yeah, I mean, salesmen sell stuff, but some of it is, it's like if you had a piece of metal in the campfire and you took it out, you'd obviously burn your hand if you touched it. But if you soak the thing under water, you could touch it and you're like, okay, that's warm, but that's not bad. If you left it alone for a little while and came back to it and tried to touch it, you'd burn yourself again because the heat from the inside made its way to the outside. The same way you can't cool the outside of that shell and cool off the windings and the guts inside that compressor. You're gonna be there half a day trying to cool that down. And water hose doesn't work. Back in the day, we even sprayed them with refrigerant, which absolutely do not do that now, but that's when nobody knew any better. And yeah, you'd hose them down with refrigerant, and that didn't work, incidentally. So you're just wasting refrigerant. So the real fix is pull the disconnect, don't tell the customer what you did, come back the next day. Okay, so here is more of an exploded diagram of what's going on inside that overload. It's just, a little basic thermal switch that when it gets too hot, it opens up a set of contacts so that it doesn't let you know what's going on in there. Okay, so what's wrong with this compressor? Run to common, 0. Start to common, 0. Run to start, 0. Yeah, bad windings. Bad windings, and there's no fix for that. And incidentally, on the two-stage compressors that we have out there, where they'll have the electronics connected, they'll have the high voltage connected on one side, and then they'll have a plug like this on the other side. That is to open and close an unloader on that compressor to make it first or second stage. And a weird little thing about these is they're 24 volts AC, but then the AC is transformed into DC right before it goes into that thing. So you have to check and make sure that the connector is actually outputting DC, so it will actually work that. If you find out that it's putting out the proper amount of DC and you plug it in there and it won't switch over that unloader, then that compressor is half bad. You got to get a new compressor. So as long as it's outputting the correct 24 volts DC that it's supposed to do, and it's not, and because usually you will hear a tone if that thing is running and you unplug that connector and plug it back in, you'll hear it go, it'll have a difference in tone to it. So that's how you know if that thing is acting up or squirrely. And if it turns out that the shell is nice and cool, it's compressing just fine, it just won't switch into the second stage, then it's a bad compressor. Even though it works, it's a bad compressor. Because there's no fixing it, because all of that electronics is inside the compressor. So we have a couple of examples. Is the first one shorted or is the second one shorted? So if when you check your compressor, you're going to want to go to the bare copper on the compressor. That's where you're going to put one of your leads on. Set your meter for continuity so that you can hear that tone, the beep, when you got your meter going on. So put one on the bare copper and then touch your other meter lead to all of these different points. And if you hear that tone anywhere, you're essentially having this, which is you have a winding shorted to the case of the compressor, and that compressor is no good. This one's fine because at least it's not shorted to ground. We don't know if the windings are good inside of it, but we know it's at least not shorted to ground. A lot of times when you get a burnout situation where you get a lot of acid buildup, you'll have a compressor that is shorted to ground. The windings check out, but the compressor still won't start. Why not? Could be low voltage, could be capacitor, could be that the rotor and stator inside the thing are too tight. It could be a bad contactor that's just not sending enough juice to it. It could be broken internally. Sometimes they just won't start. Sometimes you can hear them and they rattle like ball bearings flying around, and then you know the thing is bad. So one of the things you're going to do is you're going to check to see if you have got proper 230 volts to your compressor, because as our friend Mike Grulich is fond of saying, 115 to ground won't make it run. A lot of times, especially if you have a shunt in your system, you can get electricity going from one line through this through the other stuff and coming back on the same line. So if you're checking for 115 to ground, you'll have 115 on here and you'll have it on here when that contactor is energized, but it's still not 230. It's the same 115, it's just making a circuit and coming back. So you're measuring the same side of power twice. So that could be because of a blown fuse. That could be because of windings, all those other things that we said that it could be. But 115 to ground on either leg is not going to make it work. So you got to make sure you have your 230 volts at your compressor, and then you'll know whether or not that thing is going to start. Testing three-phase voltage imbalance. Never operate a compressor where there is an imbalance in supply voltage greater than 2%. And use the formula on the next page to determine the total percentage of imbalance. So we're going to take our three supply voltages. In this case, we're working at 460 volts, three-phase, 60 hertz. And we're checking for our voltage between A and B, A and C, B and C. And we're finding we've got these three different voltages on there. They're close, but are they close enough so that they're going to be fine? So here's our formula. We take all three of those voltages, we add them together, and because there were three different voltages, we divide by 3, and that will tell us what our average voltage is. And that average voltage then we compare to each of the voltages that we got off of the separate lines to see how much of a deviation we have. So in the first line, between the 252 volts and the 457 volts, that's a 5 volt difference. The 464 volts to the 457, that's 7 volts. 455 to 457, that's only 2 volts. So our maximum deviation is 7 volts. So to look for the voltage imbalance, we're going to do this little formula. 100 times 7, which was our maximum voltage deviation, divided by our average voltage times 100, and that gave us 1.53%. And 1.53% is less than 2%, so those voltage differences, they're okay. They're all right. There's nothing wrong with that. If they were larger than 2% voltage imbalance, then you've got a problem, and you've got to talk to the homeowner about talking to the power company.
Is my thinking right? You could just take the 457 and multiply it by 2%, and it's going to give you a number, and if all your other numbers are less than that number, you should be good, right?
Show off. So yeah, that's one way of doing things.
Well, you remember that in the field. Just so you know.
Okay. So, okay. So why do we care about voltage imbalance? We could have unexplained motor thermal protection trips, premature failures of motors and thermal protectors, excessive motor operating temperatures, breakdown of compressor lubrication, and different types of electrical failures. You want to switch, or you want me to keep going? Yeah, let's go ahead and take a 5-minute break, and then we'll come back, and there will be a different face at the podium.
My math was correct.